It is 1 o'clock in the morning on April 14th, 1970, and a row of men in Houston are staring at numbers that will kill 3 people if nobody fixes them in the next 4 hours. These men are not astronauts. The average age inside mission control during the Apollo program was 26. Some of them have been awake for 30 hours. The room they're sitting in is called the trench. It is a sunken row of consoles at the front of mission control, where the trajectory specialists work, close enough to the main screen that the controllers can read the numbers without standing up. The ceiling is low. The ashtrays are full. Every console has a direct line to the spacecraft. And right now, every number on every screen in that room is wrong. 200,000 miles away, Apollo 13 is drifting. An oxygen tank exploded 90 minutes ago and tore through the service module, which means the main engine is almost certainly destroyed, which means the only vehicle that can get Jim Lovell, Jack Swigert, and Fred Hayes home is a lunar module that was never designed to do what it's about to be asked to do. You know Apollo 13. You've seen the movie. But the version most people carry around in their heads is about 3 astronauts improvising their way home through willpower and ingenuity. While that version is true, it's also incomplete, because the improvisation didn't happen in the capsule. It happened in a room in Houston by men whose names never made the poster, solving a math problem that had never existed before, on computers that weren't built to solve it. This is what actually brought Apollo 13 home. 40 minutes after the explosion, a flight controller named Jerry Bostick ran the numbers for the first time and didn't like what he found. Bostick was the Flight Dynamics Officer, short for FIDO in mission control language, and his job was to know exactly where the spacecraft was going at all times. What he was looking at told him Apollo 13 was going to miss Earth by 2,600 miles. To understand what that number means, picture this. The re-entry corridor, the narrow window of atmosphere the capsule has to hit on the way back, is roughly 2 degrees wide. If the re-entry is too steep, the heat shield will fail and the capsule burns. Too shallow, and the capsule skips off the upper atmosphere like a stone off water and keeps going. 2 degrees, that's the margin. But on the current path of Apollo 13, it was not even going to come within 2,600 miles of that window. The mission's original plan had the spacecraft on a hybrid trajectory, not a free return path around the moon, because the landing site required a different approach. That deviation is what made the miss so large. Getting the spacecraft back onto a free return trajectory meant firing an engine, and the main engine on the service module was almost certainly wrecked. The only engine left was the descent engine on the lunar module, a small, throttleable engine designed to lower 2 astronauts gently onto the surface of the moon. Nobody had ever used it to navigate a crippled spacecraft back toward Earth. Nobody had programmed the computers in Houston to calculate what that maneuver would even require, because nobody had ever thought they'd need to. So Bostick and his team started doing it by hand. The first burn, the one that gets the spacecraft back onto a free return trajectory, had to happen fast, before Apollo 13 swung around the moon. Charles Deiterich, the retro fire officer sitting beside Bostick in the trench, worked the calculations while the rest of mission control kept the crew alive. Lunar module systems were being powered up on a timeline that normally took 3 days and was now happening in 45 minutes. Procedures that existed in no manual had to be written from scratch and read up to the crew over the radio, while Deiterich was still running numbers in the background. The temperature inside the capsule was already dropping. The crew had moved into the LM to save what little power remained in the command module for re-entry, the one moment they'd need it. And the question of whether any of this math would actually work was something nobody could fully answer yet. The first burn worked. Apollo 13 swung around the moon and came back out the other side still breathing. But Bostick already knew that wasn't enough. If you want to understand why, here's what the crew's situation looked like after that first burn. They were alive, and they were pointed at Earth. But at their current speed, they wouldn't reach home for 4 days. The lunar module carried roughly 2 days of oxygen and power for 2 people. There were 3 people inside it. The math there is straightforward and ugly. Deiterich had already started working on the calculation that would actually save them. A burn so precisely designed that it would cut 10 hours off the return trip, shift the splashdown point from the Indian Ocean, where there were no recovery ships, to the Pacific, where the USS Iwo Jima was already moving into position. The Indian Ocean detail matters more than it sounds. A splashdown there wasn't just inconvenient, it was effectively a death sentence. The recovery infrastructure for Apollo missions was built around the Pacific. Ships, helicopters, medical teams. None of that existed in the southern Indian Ocean in April 1970, and there was no time to move it. Getting the splashdown point wrong by that margin wasn't a logistical problem. It was the same outcome as not coming home at all. This calculation is called the PC+2 burn. 2 hours after the closest point to the moon, the lunar module's descent engine fires again for a precisely timed duration, at a precisely calculated angle, and does something an engine that size was never meant to do. It reshapes the entire trajectory of a spacecraft carrying 3 people home from 250,000 miles away. The burn would last 4 minutes and 23 seconds. Every decimal in Deiterich's calculation had to be correct, because there was no margin to correct it afterward, and no fuel budget for a second attempt. Deiterich ran those numbers through the night. If you want to subscribe, now is a good time. We aim for 2 videos every week. The PC burn was scheduled for April 15th. Jim Lovell had been awake for the better part of 2 days. The temperature in the lunar module had dropped to 38 degrees Fahrenheit, and condensation was forming on every surface. Lovell, Heise, and Swigert were rationing water to 6 ounces a day each because the fuel cells that normally produced water as a byproduct were dead. Carbon dioxide was building up in the cabin faster than the scrubbers could handle it, which is why Mission Control had spent part of the previous day talking the crew through building a makeshift adapter out of a plastic bag, a flight manual cover, and duct tape to fit the command module's square CO2 canisters into the lunar module's round filter housings. The procedure didn't exist anywhere. Engineers at Houston built it on a table using only the materials they knew the crew had on board, then read the steps up over the radio one at a time. The finished adapter looked like something from a kindergarten craft project. It kept 3 men breathing, but it illustrated exactly how far outside any planned scenario this mission had already traveled. Here is the problem Deiterich's perfect calculation now faced. The lunar module's guidance computer had been powered down to conserve electricity. It had been off for 20 hours. When you restart a navigation computer after 20 hours of drift in space, it doesn't know where it is anymore. It has to be told. That data had to come from the command module's navigation system, which Lovell had to read manually, transfer to paper, and then enter by hand into the LM's computer. If any number in that transfer was wrong, the burn would point them in the wrong direction. Not the wrong direction slightly. The wrong direction in a way that no further correction could fix. Lovell did the math himself, in a 38-degree capsule with a pencil, checking his figures against the numbers Mission Control was reading up to him over the radio. Before he could enter anything into the guidance computer, he had to manually realign the LM's navigation platform, by sighting known stars through the capsule window, a process that normally the computer assisted with, now done entirely by eye. He had been an astronaut for 9 years and a naval aviator before that. He had flown Gemini 7 and Gemini 12 and orbited the moon on Apollo 8. None of that made the arithmetic easier to trust when he was the one checking his own work. He had to trust his own arithmetic at the moment, when arithmetic was the only thing between his crew and a trajectory into permanent solar orbit. The burn lasted 4 minutes and 23 seconds. When it was over, Bostick ran the updated trajectory numbers and confirmed what Deiterich's calculations had predicted. Apollo 13 was coming home. They would reach Earth in roughly 38 hours. The splashdown point was the Pacific. The Iwo Jima was already there. One problem remained. Re-entry requires an extremely specific angle. The corridor hasn't changed. It's still roughly 2 degrees wide. Still the same brutal margin between burning and bouncing. Apollo 13's path needed one final small correction before it hit the atmosphere. A burn of 14 seconds that would nudge the angle just enough to thread that window. The onboard computer that would normally time and execute that burn was offline. The digital mission timer had been powered down to save electricity. There was no automated system available to count 14 seconds and cut the engine. Jack Swigert timed it on his wristwatch. The burn was exactly 14 seconds. The angle was correct. On April 17, 1970, Apollo 13 hit the atmosphere at precisely the right trajectory and splashed down in the Pacific Ocean. The crew was recovered by the USS Iwo Jima. All 3 men were alive. In the trench, Jerry Bostick watched the splashdown on a monitor. He had been awake for most of 4 days. The calculation he and Deiterich and their team had built from nothing, from a scenario nobody had ever programmed for, using methods they invented over the course of a single sleepless night, had worked exactly as the math said it would. 3 men were being pulled out of the Pacific because the numbers were right. Bostick never became a household name. Neither did Deiterich. The movie gave them no speaking roles. Most people who know Apollo 13 well enough to quote it couldn't tell you who ran the trajectory calculations, or what the PC+2 burn was, or why it mattered that the splashdown point moved from the Indian Ocean to the Pacific. The crew did something extraordinary. What they did required everything they had. But they executed a plan they did not build. Somewhere behind every survival story that gets turned into a movie, there is usually a room full of people like that. People who solved the problem nobody was filming, who did the work that made the heroism possible, and who went home afterward without anyone learning their names. Apollo 13 is famous for what happened in the capsule, but it came home because of what happened in the trench. And it makes you wonder how many other moments in history turned the same way, on a calculation nobody saw, by someone nobody remembers, that the history books filed under someone else's name.